Section 2.4, the conservation of dimension. The previous section established connections about the number of pivots, rows, and columns, and null spaces and column spaces. Now we place this into both simpler and more general terms using vector space dimensions, and then we return to discussion in terms of matrices. First theorem of this section is that let V1, Vl be a basis for a vector space V over scalars F, and let U1, Uk be a basis for a subspace U of V. Then what we have is that k is less than or equal to 1, the number of basis elements in the subspace, compared to the number of basis elements in the vector space V. Also, we have that k equals to L if and only if U equals to V, and if R equals to L minus K is a positive number, then there exists a subset Vi1, Vir of the basis V1, Vl of V, such that we can extend the U basis of the subspace U1, Uk, adding these Vi1, Vir, we extend it to a basis of the whole space V. So the proof, since U is a subspace of V, that means that each vector Uj in this basis of U can be expressed as a unique linear combination of the vectors in the basis for V, which means U sub j equals to some sum as I goes from 1 to L, Aij Vi, where j goes through the indices of the subspaces, basis from 1 to k. So we have two indices for A now for the coefficients. One is for the running index, I going from 1 to L, and then also for each of these Uj entries we have j index. And that means that we can collect all these Aij entries into a big matrix with L rows and k columns. And then we will use this lemma about null spaces that said that if you have a P by Q matrix and if the null space of A is 0, then the number of rows should be greater than or equal to the number of columns. So for that we have to show that the null space of A is 0, or it contains only the 0 vector. So let's assume that we have an x vector in the null space. That means that Ax is 0 vector by the definition of the null space. Let's write out the general ith entry of this Ax vector. So the way we multiply the matrix A with the vector x is that the ith row multiplied with the x column vector gives us the ith entry in the Ax multiplication. So this means then the ith row, and then we go through the ith row in each entry, so that means the sum as j goes from 1 to k, Aij xj, and that's supposed to be equal to 0 because x is in the null space for each I going from 1 to L. Then we look at this following linear combination. The sum as j goes from 1 to k, xj, uj. So instead of the x entries, we have the uj vectors here. That's a linear combination of the basis vectors in the U subspace. And then we can replace the uj with its expression in terms of the V basis elements. And because these are finite sums, we can change around the summation arbitrarily, and we can multiply through with the scalar xj. And what we get here, after combining together these coefficients, is that we have I going from 1 to L, then j going from 1 to k, Aij xj, that's a scalar, times the vector Vi. And since x is in the null space of A, that means this coefficient is actually 0 for each vi, going from 1 to L. That means we are multiplying each vector with the 0 scalar, so the result is a 0 vector. And then what we have is that since the vectors u1, uk is a basis, they form a basis because they are linearly independent in U, then that means that the only way to get, as a linear combination, the only way to get the 0 vector, if it's a trivial linear combination, that means all these x1, xk coefficients should be 0. But these are the entries of x vector, so that means that the whole x is a 0 vector. And that means that the whole null space is just the 0 vector. Because we obtained that if any x is in the null space, that's the 0 equals to the 0 vector. Then we can use now the lemma that says that we have to have at least as many rows as the number of columns. So that means L is greater than or equal to k. Or k is less than or equal to L, which is exactly the first part of the theorem. Next, we show that k equals L. First of all, it's supposed to be if and only if u equals v, but first we show implication in one direction. And we prove that k equals L implies u equals v using proof by contradiction. So we show that k equals L and u not equals to v is false or impossible. So u is the span of u1, uk, and if it not equals to v, then that means that there is a vector w in v such that it's not in the u subspace. And that means that w is linearly independent from these basis vectors u1, uk of the subspace U. Then this in turn implies that if you put together the span of u1, uk and w, that's first of all a subset of V, and then we can use part 1 for this new subspace, the span of u1, uk, w, let's denote it with u star, which is a subset of V. And according to the first part of the theorem, this is just another version of it with one more vector for the basis of U. And it says that that should be less than or equal to L, the number of the vectors there. But now the number of vectors is k plus 1. So we have that k plus 1 should be less than or equal to L. This is contradiction because we have that k equals to L. So that means that k equals L does imply that u equals to v. To prove the other direction, that u equals v implies that k equals to L. If u equals v, then every vector vj, j goes from 1 to L, can be written as a linear combination of basis elements u1, uk, because the basis of u is then the basis of v. And then again we can use part 1, but now u and v interchanged, because we can say that, well, then v is also a subspace of u, although it's called a trivial subspace because it's the whole space. And then what we get from the part 1 is that then L should be less than or equal to k. But we also have then k greater than or equal to L, or I'm sorry, k less than or equal to L. So that means we must have that k equals to L. For the third part, showing that if the difference between L and k is R, which is a positive number, then we can find, we can extend the U basis into a basis of V by adding some extra basis vectors from V. And the number of those basis vectors should be R. So to prove this, if L minus k equals to R is positive, then that means that L is not k. And then part 2 implies that U is not V. That means at least one of the vectors in the basis, say vi1, is not in U. So that means that if we add to the k U basis vectors this vi1 vector, which is not in U, then this is still a linearly independent set of vectors in V. then if this r, L minus k equals r, is larger than 1, then that means that there must be another vector vi2 in the basis, that is in the v basis, that is not in the previous span. And then we can add this to the set and to have a linearly independent set still inside the vector space V. So if r is larger than 2, then we can continue this process, but clearly we cannot continue more than r. Once we add r vectors, then we get that this set u1, uk, vi1, vir is basis for V. So definition 2.27, this preceding theorem guarantees that if V is a vector space over F, over the scalars F with a finite basis, then every basis of V has exactly the same number of vectors. So this is the third part, basically, that says that we can extend the basis. Any linearly independent set we can expand to a basis, and k plus r will be exactly L, the number of original basis elements in V. So this number, this unique number for each vector space, the number of basis vectors, this is called the dimension of the vector space. And if we have a vector space, the trivial one with only the 0 vector in it, this will be assigned the number of 0 for the dimension. If the basis is not finite, then V is called infinite dimensional vector space. So let me remind everybody that empty set is not a vector space, and hence it doesn't have a dimension. Let's see an example here. We looked at straight lines in one of the homework assignments. If you consider the vector space U, which is the span of the 1, 4 vector, that means it's the set of all vectors in the form of alpha times 1, 4, where alpha is a real number. So this is all the linear combinations of this one single vector. Then what we get is xy vectors such that y equals to 4x, where x is any real number. So this is a straight line, y equals to 4x, is a straight line through the origin with slope m equals to 4, and we have that this is a one-dimensional vector space, because we have one basis vector 1, 4. Of course, you can find many other basis vectors, but any basis has just one vector. And this also shows that if you only have the 0 vector that shouldn't have dimension 1, it must have dimension 0, because this is kind of one point, the 0 point. Let's consider V as the polynomials P of lambda. We looked at this example before. So this has the form, the sum as j goes from 0 to n, aj lambda to the j, where aj is a complex number and j goes from 1 to n. So this is the space of polynomials of complex variable lambda with complex coefficients alpha j and with degree less than or equal to n. So the power of lambda is maximum n, or the largest power in these polynomials. This is a vector space with the natural rules of addition and scalar multiplication for polynomials. We looked at it before, and you can see that one lambda square all the way up to lambda n is a basis. Even the definition here shows that what we have is the linear combination of all the basis elements from 0 power, which is just 1, to the nth power of lambda. So we see that this is actually n plus 1 dimensional. Since we start with the 0 power and it goes up to n. So altogether n plus 1 basis elements. We can modify this, the set of polynomials or the vector space of polynomials. So instead of saying that the degree is less than or equal to n, let's say that any degree polynomial can be put into this set P. So polynomials of degree, arbitrary degree, with complex coefficient and complex variable lambda. It's an infinite dimensional vector space, since if you start writing down the basis, 1 lambda lambda n, it never stops because it's supposed to contain all the powers. Since you can have a polynomial with arbitrary large power. 1 million, 100 million, a billion power, doesn't matter. There is no highest degree polynomial because all the possible polynomials are there. So because you have to continue forever with these basis elements, that means it's infinite dimensional. Next lemma, let T be a linear mapping from a finite dimensional vector space U over F into not necessarily finite dimensional vector space V over F. Then the dimension of the range of the transformation T is less than or equal to the dimension of U. So this is interesting that the dimension of range, although the range is in the vector space V, and V could be infinite dimensional, still it shows that the range will be always finite dimensional if we are mapping from a finite dimensional vector space U. The proof, by the definition of the range RT, for any V in the range, there exists a U vector in U such that V equals to T of U. Let's say that we have a basis U1, Un for the U vector space. N is the dimension of U then. And then U can be uniquely written, this U vector, as a linear combination of the basis vectors of U. That means U is the sum as I goes from 1 to n, Ci Ui, where Ci is some scalar. Then V, which is the image of T under U, so T of U, we can replace here U with this linear combination. And then because T is linear, we can take T inside, and also we can factor out the Ci's. So we get that the sum as I goes from 1 to n, Ci times T of Ui. What does it mean? So that means that the range, where V is an arbitrary vector, any vector in the range can be written as a linear combination of the TUI vectors. So that means the range is a subset of the span of the TU1, TUN vectors. And that means then that the dimension of the range must be less than or equal to n. We don't say whether it's linearly independent or not, this set, but definitely the dimension of R of T cannot be more than n, which is the dimension of U. So this finishes the proof. The big theorem of this section is the so-called principle of conservation of dimension. That says that let T be a linear mapping from a finite dimensional vector space U over scalars F into a finite dimensional or not vector space V over the scalars F. Then the dimension of the null space of T plus the dimension of the range of T equals to the dimension of U, the space where we are mapping from. The interesting thing here is again that the range is the set of images in V, but actually the dimension is related to the dimension of U, and the null space is in U, so that's easier to understand why this dimension of the null space is related to the dimension of U, but interesting thing about this, the dimension of the range. So due to the previous lemma, we have that R of t is finite dimensional, even if V is infinite dimensional. That means that we don't have to worry about whether or not this makes sense here. Then the first case is that we suppose that null space is not zero. So we have to work with two spaces, the null space and the range. And we considered cases depending on whether one of them is zero or the other is zero or none of them is zero. So suppose that the null space is not zero and not the zero vector, and the range is also not trivial. That means that their dimension is not zero, so let's say that U1, UK is a basis for the null space of T, and V1, VL is a basis for the range of T. And then we choose vectors Y sub j in U such that Vj equals to the T of Y sub j image. Since these basis vectors V1, VL is in the range, that means there should be such Y's as j goes from 1 to L. Then the claim is that the set U1, UK, Y1, YL is linearly independent. So let's look at this. What if we have a linear combination of U1, U's and Y's, such that this is a zero vector with some scalars alpha 1, alpha k, beta 1, beta L. Then if you apply the transformation to this, then what we have is that this is the T transformation of the zero vector, which means this is zero. Since it's a linear map, the image of zero is always zero. And then from here, if you write this down, starting from the left with 0 and T of the two sums, because T is linear, we can split this right-hand side up into two sums, and also we can take T inside and apply directly the UI vectors and the YJ vectors. Then U's are for the basis, from the basis of the null space. So that means T of UI is 0. And this whole first sum is 0. So we are only left with the second sum. Now in the second sum, the T of Yj equals to, that was the choice of Yj's, equals to Vj. So this is the sum as j goes from 1 to L, beta j, Vj. But these V vectors from 1 through L is a basis, and that means that the only way that this linear combination is 0, because the V's are linearly independent, is if it's a trivial linear combination, which means B1, BL are all zeros. So then, going back to this equation, this second part is 0 because all the B's are zeros. So that means that the first part, the sum of alpha I, ui, as I goes from 1 to k, must be the zero vector. But then what we have is that the U's are also basis. They also form a basis. Hence, if this is true, then the only way for this is to be true is that all the alphas are zeros. That means that only the trivial linear combinations of U1, UK, Y1, YL produces 0, because both alphas and the betas must be 0. And that means that this set is a linearly independent set. For basis, we also need that the span of these vectors equals to the whole space U. So we show this by choosing an arbitrary W in U. Then we have that when you apply T to this W, this is in the range, and that means that you can write it as a linear combination of the basis elements in the range. So it's TW equals to the sum as j goes from 1 to L, Cj, Vj. Then using the definition of y, the v's are t of y with indices j. So we can replace Vj with t of yj. And then we can rearrange this equation to 0 on the right hand side. We get t of w minus the sum as j goes from 1 to L, Cj, t, yj equals to 0. Then applying the linearity of the transformation backward, we can take it outside the sum and difference. So we get the t of w minus the sum Cj, yj equals to the 0 vector, which means that this vector w minus the sum Cj, yj is in the null space of T, because when you apply T to it, it equals to the 0. And if it's in the null space, then that means that this can be written as a linear combination of the null space basis vectors ui with some scalar coefficients d1, dk. And then from here we can rearrange it and we get that w is the linear combination of ui and yj elements. So this means that any vector w of u can be written as a linear combination. So the span of these vectors u1, uk, y1, yl must be at least as large as u. Of course, we have that all these vectors are in U, so that means that the span must be also in U. And with this, we get that the span equals to exactly U. Then we have that the dimension of U is k plus L, because this is the number of basis entries. And that's exactly the dimension of the null space of T plus the dimension of the range of T. That was the definition of K and L. We are finished with the first case, where we assume that neither the null space nor the range are just the 0 vectors. Now we suppose that the null space is only the 0 vector and the range is not just the 0 vector. The proof is similar to the previous case. Let's go through it still, just to practice how to construct the proof. So in this case, we have v1, vl as the basis for the range. One possible basis, and then we choose vectors yj in U such that these vj's are the images of yj's. Then the set y1, yl is linearly independent. Suppose that we have a linear combination, sum j goes from 1 to L, beta j, yj, 0, with some scalars b1, bl. Then we apply T to both sides of this equation and we get that T of 0 is 0, so that means T of this linear combination is 0. And then from here what we get is that we can again take the T inside the sum, so we get T of yj's inside the sum, which is Vj, and we have that this linear combination of vj's is 0, but we have that v1, vl is a basis in the range. That means all these betas must be 0. That means that y1, yl is linearly independent. We also have that the span of this is u, the span of the y vectors, because if you have any w vector in u, then we have that t of w is in the range. That means that we can write it as a linear combination of the vj's, because those are the basis vectors in the range. But according to the definition of the y's, vj's can be replaced with t of yj's. Then we rearrange this sum to get t of w minus the sum cj t yj equals to 0 vector. And then we can again factor out the same way as in part 1, t from this sum on difference, and that means that w minus cjyj is in the null space, because when you apply t to it you get the 0 vector, but the null space is only the 0 vector, so we have that this whole thing is the 0 vector, and that means that this arbitrary w element of u can be written as the sum of linear combination of yj's. That means the span of the y's equals to u. We have L of these, and that means that the dimension of u is L. This is great because then L can be written as 0 plus L, where 0 is the dimension of the null space and L is the dimension of the range of T. So this case is also done. The third case is when we have the range of T is the 0 vector only. And then what we have is that the null space is the whole U, because actually everything, all elements of U goes to 0 according to that. And we have that the dimension of U is just K, where K can be written as K plus 0. K is the dimension of the null space, and 0 is the dimension of the range. So this finishes this proof. We skip the next section 2.5 about quotient spaces, because this is just another approach to establish the previous theorem. And quotient spaces is more theoretical than applied linear algebra. Next section 2.6 is about conservation of dimension for matrices. So this is an application of the conservation of dimension theorem. We now consider particular linear transformations T from Fq into Fp that can be defined by multiplication of vectors with a matrix A. So typically this is what we do. In this case, use matrices for linear transformation. And this is really a corollary of the previous theorem, but because this is so important for using it for matrices, we write it down again. So what we have is that if A is a P by Q matrix, then the null space of A, which means that all the x Fq vectors that for which Ax is equals to the 0 vector, this is a subspace of the Q vectors. And the range of A is the set of all Ax vectors, where x is a Q vector. This is a subspace of the P vectors, vector space. And what we have is that the Q, which is the number of columns, is the dimension of the null space of A plus the dimension of the range of A. So if you look at the previous theorem, how this compares to it, we are mapping from U vector space, and the dimension of the null space and the range equals to the dimension of this U space. In our case, the U space is the set of Q vectors. Since this is how the transformation can be defined, that T of x is A times x. And for A times x, for the multiplication to make sense, x has to be a Q vector. And the dimension of the vectors with Q components is Q. As a kind of quick application of this, there is a so-called rank of a matrix A, which is a P by Q matrix in general. So this is denoted by the rank of A, and there are different ways of defining it, but all of these are equivalent. So we could say that this is the number of pivots in its reduced echelon form. But then based on the previous theorem, we can also say that the rank of A is the dimension of the range of A. Next, let's consider a lemma. If A is a P by Q matrix and C is a Q by R matrix, then the rank of A times C, notice that A times C makes sense because the Q's match up the dimensions. So the rank of A times C is less than or equal to the rank of A, and we have equality if C is right invertible. So let's see how to prove this. If Y is in the range, the rank is about the range. If we have a vector in the range of AC, then that means that there exists an X R vector such that Y equals to AC times X. That's what it means that Y is in the range of AC, that it can be written as AC times X for some vector X. But then, if you just look at the Cx part of this multiplication, V equals to Cx, that's a Q vector because C is Q by R. So the resulting vector, when you multiply C with X, will be the number of rows in C, which is Q. And what we have here is that then Y equals to A times C times X is the same as A times V, where V is C times X. But then when you look at this, that Y equals to A times V, that means Y is in the range of A. So we get that the range of AC is a subset of the range of A. And that means then that the rank of AC is, which is the dimension of the range of AC, is less than or equal to the dimension of the range of A, which is the rank of A. Since a smaller vector space, we have a smaller dimension, or possibly equal. If C is right invertible, then there exists B matrix, must be R times Q size, such that C times B equals to the Q by Q identity matrix. This is QR, RQ. When you multiply, you get the Q by Q matrix. And then what we have here is that if Y is in the range of A, then there exists a VQ vector such that Y is A times X. The X vector, of course, can be written as the identity matrix times X. And since X is that was supposed to be X vector. So X is a Q vector. The identity matrix must be Q by Q. But the invertibility means that the identity matrix is actually equals to C times B. So X is C times B of X, which means it's C times BX. And that means that Y, which was A times X, can be written as A times C times B times X. But then that means that Y is in the range of AC, since it can be written as AC times a vector BX. And that means that the range of A is also in the range of AC as a subset. So we get the opposite inequality, that the rank of A, which is the dimension of the range of A, is less than or equal to the dimension of range of AC, which is the rank of AC. And then this, with the previous direction of the inequality, gives us the equality that the rank of AC must be equal to the rank of A. So the next theorem is that if A is a P by Q matrix, then we have several of these statements. First of all, we have that the null space of AHA equals to the null space of A. AH is the Hermitian transpose of the A matrix, which means it's conjugated transpose and complex conjugation. We also have that the range of AHA is the same as the range of AH, And we have that the rank of A is the same as the rank of AH, and both of these are less than or equal to the minimum of P and Q, the number of rows and number of columns. So for the proofs, we check what if X is in the null space of AHA and Y equals to A times X. Then we have that the sum, as j goes from 1 to p, yj modulus square can be written as the yh times y vectors. So check this, that exactly gives us this entry by entry multiplication, but with the complex conjugate. And that's the modulus square. So that's something you have to know, that if you multiply together a complex number with its complex conjugate, you get modulus squared. And we go through this entry by entry with j going from 1 to p. But then YH, the Hermitian transpose, can be replaced with AXH, and Y can be replaced as AX. We saw this before. Let me remind everybody that when you have the transpose and also the Hermitian transpose of a product, if you apply this factor by factor, then you have to change the order. So this becomes XH times AH, and we had A and X. If you combine together this or regroup this to get AHAX, then since X is in the null space of AHA, that means this part is 0. So we are having a multiplication of XH with the 0 vector, which means this becomes the 0. So what we have here is then that AX, which is the Y vector, equals to the 0 vector. That's the only way that the sum of the component square modulus is 0. And then that means that we have shown that X is in the null space of A. So we have that the null space of AHA is a subset of the null space of A. The other direction, if X is in the null space of A, then AX equals to 0, and then also we have that AH-AX is AH-AX, where AX is 0, so that means this will be 0. And that means that X is also in the null space of AHA. With this we get that the null space of A is a subset of the null space of AHA, and together with this other inclusion we have the null space of AHA equals to the null space of A. Then we can apply now the principle of conservation of dimension. First we apply it to the A matrix, which is a P by Q matrix. This is mapping from the Q vectors, so the dimension of that is Q, and according to the principle of conservation of dimension, this Q equals to the dimension of the null space of A plus the dimension of the range of A. We can also apply this to the AHA vector, which is also, it's a Q by Q matrix, so that means it's also mapping from the Q vectors as a multiplication. So we can use again this principle, Q equals to the dimension of the null space of AHA plus the dimension of the range of AHA. We also have that the null space of AHA is the same as the null space of A. So then comparing these two, we get that comparing the two different sides and using that the null space of A is the same as the null space of AHA, we can cancel the same terms on the two sides, and we get that the dimension of the range of A is the same as the dimension of the range of AHA. This is actually not what we had to show so far, but then we can use the same lemma as before, and the previous lemma that says that if you multiply A from the right with a matrix, the new matrix will have rank less than or equal to the original rank of the matrix. So then we use now C for C the A matrix, and for A we use the AH matrix, and then the previous lemma says that the dimension of the range of AHA is less than or equal to the dimension of the range of AH. So comparing these two equations, then what we get is that the dimension of the range of A is less than or equal to the dimension of the range of AH. Combining these two together. But then we can replace A with AH and AH with A to get, well, actually we don't have to replace A with AH. What we get is that if in this one, if we replace A with AH, we get that the dimension of the range of AH is less than or equal to the dimension of the range of AHH, but the Hermitian transpose applied twice is the same as applying the transpose twice, which means it's the original matrix, so that equals to the dimension of the range of A. And then with these two together we get all the inequalities saying that the dimension of the range of AH is the same as the dimension of the range of AHA, which is the same as the dimension of the range of A. So we also have the inclusion that the range of AHA is a subset of the range of AH, since the image of AHA automatically is in the image of AH. And then that means that we have to have equality that the range of AHA is exactly equal to the range of AH. Finally, since the range of A is in P vectors, since when you multiply P by Q matrix with a Q vector, you get a P vector. That means that the rank of A, which is the dimension of the range of A, is less than or equal to P, the number of rows in A. And similarly, since the range of AH is inside the Q vectors, since AH is a Q by P matrix, we have that the rank of AH, which is the dimension of the range of AH, is less than or equal to Q. And because these are the same, the rank of A and the rank of AHs, that means that they have to be both less than or equal to P and less than or equal to Q, so they are less than or equal to the minimum of P and Q. And that finishes this section.